Waiting to be live on YouTube. How is the feedback by students? So waiting to be
yeah, maybe one of the class moderators like Judy or Wijdan can explain, because they received the questions and feedback from students. So
yeah, that will be great to receive some feedback.
Good evening, Dr. Ibrahim. I don't know if it's good evening or good morning or good afternoon in Canada. So from our place, good evening, okay?
Thank you.
So as a moderator for class 4, we received a couple of feedbacks about the assignment. One of them is that some of them had a problem with uploading it, one of the issues. Second thing is that some of them could not be fully solving the question. They tried the best, but they couldn't do it all. Okay. Another point is that some of them said that due to our background, which is not related to physics, we weren't able to understand the lecture properly and be able to later on solve the assignment that has been given to us. So far, this is, I can say, a couple of feedbacks about what we received as a moderators for class 4.
Right. Perfect. Thank you.
Welcome.
Yeah. Wijdan, do you have any?
Oh, I think she's not here.
She's not there. Okay.
Yeah.
Fantastic. Let's it's very clear. The course we say that is for physicists, right? Is mathematical methods for physicists. And this is the course that when I was in third year of my undergraduate, I studied, and I understand if mathematicians they want to attend this course, they may have a different perspective. It look like more applied mathematics rather than the core hardcore mathematics, which is proving things. So I completely understand that and I appreciate the comment. Yeah. So let's start with the lecture 6, which today we will be closing chapter 1, which is a little bit long chapter. And then the next 2 weeks we will go through chapter 2, which is more coherent and also advanced in terms of mathematical tools. So so far we learned what is a scalar, what is a vector, what is a gradient, what is a divergence, curl, and also we looked into the integral formalism of that. And also we use them in physics and mainly in electrodynamics, which was solving Maxwell equations. And we derive also wave equations, if you recall. Now let's today look into another example, which is very, very interesting. So if you recall, by the way, last lecture, we also proved the Green theorem, the form 1 and form 2, which I will be using it towards the end of this lecture. So let's now go to some forces that we see in nature. So one of the forces that we discussed last time was the electromagnetic force was given by Q prime divided by 4 pi epsilon naught and R divided by R power of 3. If you remember, that was an electrostatic force, which means that while you have a charge of Q at the origin, let's assume that is X, Y, Z, and then I have another charge of Q prime here, and I want to find out which is kept at the distance of R. which of course R is a vector. So we want to understand what is the force applying to the charge of Q prime, and we say that the force has two forms: either is repelling or it will be attracting the force. So that means that either will be the direction of R or negative of direction of R. And we clarify that, well, if the product of Q prime is positive, that force will be repelling. And or let's say the force will be in the direction of R. If Q prime is negative, then force will be in the direction of minus R. And we say that the magnitude of this force is going to be 1 divided by R power of 2. So it's a Coulomb law, if from remember. So the entire of this is given inside of this equation. Okay. I think there is, we discussed that in the past, and that's what we will be using. Okay. Now let's go with another force which is very similar, and that force is indeed a gravitational force. Okay, so the force, the gravity that we have now is exerted on two objects, which these two objects, they have mass, and well, is given by minus g, the mass of the two objects, m prime, and then we have r divided by r power of 3. So remember, well, here m and m prime, they are the mass of the object. So x, y, and z. There are 2 point objects. One of them is located at the origin, I call it m, and the other one is located in another place, which I call it m prime. So the distance between these two is r. Okay, and g is the gravitational constant that we have. But in any cases, this force is always positive. It means that the direction of the force is always towards the center. So independent of m and m prime, because they are both positive. So because m and m prime, both of them, they are positive, then the force is always in the direction of minus r. Okay, so these two forces, if you look at them, the magnitude of gravitational, and this is the electrostatic, and this is the gravitational force, they are proportional to 1 divided by r power of 2. Okay, I think you heard of these forces, and people, they use it a lot. So essentially, that is given by r power of minus 2, and very, very interesting. In general, you may say that, well, any forces that I may have, it may goes with r power of minus n, so it somehow is a polynomial expansions of the distance that you may see. Either maybe by the distance, when you keep them close to each other, this force will be increasing or will be decreasing, depending on the way that you define it. But these two forces, they have one unique property. If you remember, last time, one thing that we calculated was what is happening with the gradient of r, that r multiplied by a function, or the divergence of r times a function. But here now, I will ask you, what is happening with the curl of these forces, either of them, okay? Because if I look at these two forces, the forms they have for these two forces is a constant, which can be positive, negative, multiplied by r divided by r power of 3. And now I will ask you, what is happening with the curl? of f. Okay. Can we do the calculation finding out what is going on with the curve? So, well, let's do the calculation. Curl of f indeed is given by x hat, y hat, z hat, derivative with respect to x, derivative with respect to y, derivative with respect to z of this vector, which is essentially x divided by r power of 3 with a factor of k, of course, y divided by r power of 3, and z divided by r power of 3. Do you agree? Don't forget that r is given by x power of 2 plus y power of 2 plus z power of 2 power of 1/2. So r squared is x squared, y squared, z squared. Good. Now let's do the expansions. So indeed, k is given by x component. Some students also, they asked last time about the curl. So look, how do I calculate these matrix? So essentially, I take a first component of that. It is x. The position is 1, 1. So the coefficient will be -1 power of 1 plus 1. And then the result will be a derivative of y of z r power of 3 minus the derivative of z of y divided by r power of 3. And the second term will be the position of these y will be 1 and 2. So it means that you have -1 power of 1 plus 2. Then you have y hat. Now you take the derivative. It's the derivative of x of z divided by r power of 3. Then minus derivative of z of x divided by r power of 3. And in the same way, you get the other one, which is -1 power of 1 plus 3 of z hat. And the coefficient is indeed given by derivative of x of y divided by r power of 3 minus derivative of y of x r power of 3. Okay, so let's take the derivative. So that is a k, the factor that you have it at the front, x component. So z is constant with respect to y. So what you will get z derivative of y of r power of -3. Then y also is constant with respect to z. You will get y derivative of z of r power of -3. And in the same way, let's just simplify this. The coefficient will be, that is -1. -1, it will be switch inside. So it will be y. That will be derivative of z of x derivative r power of -3 minus z derivative of x of r power of -3, then plus z hat y derivative of x of r power of -3 minus x derivative of y of r power of -3. Okay. Now, what I have to do, I have to take the derivative of r power of -3 with respect to one of the component, let's say x. And we know that is identical for y, identical for z, and we can calculate it. So this means that I take the derivative of x squared plus y squared plus z squared power of -3 divided by 2. That will be equal to -3 divided by 2. Then the derivative of these will be 2x. Then I have x squared plus y squared plus z squared power of -3 divided by 2 -1. So if you simplify this, that will be -3x. And that one will be r power of -5. Okay, so the result of this indeed is minus 3x r power of minus 5. So for that one, that will be minus 3y r power of 5 minus 5. The same for that one will be 3 z r power of minus 5. That will be 3 z r power of minus 5 minus 3 x r power of minus 5, the same way, minus 3 x r power of minus 5 minus 3 y r power of minus 5. Lovely. So I can factor out the minus 3 and also r power of minus 5. Then what I will get x at z multiplied by y minus y multiplied by z plus y x z minus zx plus z hat yx minus xy. So what you will see that that term is equal to 0, that term is equal to 0, that term is equal to 0. So indeed, curl of f is equal to 0, which is wonderful. Okay, so if the force is such a formalism, such a form, which essentially is going with k r divided by r power of 3, then definitely what I will get, curl of f is equal to 0. So for gravitational waves or gravitational force, and also for electrostatic, what I will see that the curl of f is equal to 0, which is wonderful. So in the Q&A, can you type for me, when the curl of A is equal to 0 in general? Now I'm talking about a general question. Curl of a vector is equal to 0. What is the form of vector? What can be the form of vector? People, they say that is conserved. Well, I'm not looking for the conservation. Now I'm talking about the general. So curl of f is equal, curl of v is equal to 0. And people, they say that you can write it as a gradient of a scalar. Yes, I can write it as a gradient of a scalar with a minus sign. Do you remember that we discussed about the minus sign, right? Okay. Yeah, but well, some people, they have a question regarding this. So of course, that will be minus x squared plus y squared plus z squared power of minus 5 divided by 2. Okay, that will be written as x squared plus y squared plus z squared power of 1/2 multiplied by minus 5. What is that? Is r. So it will be r power of minus 5. Okay. So going back to the question that we had here, so when the curl of a vector is equal to 0, then I can write this vector as a minus gradient of 5, a scalar. Lovely. So in this specific case, when force is given by k r divided by r power of 3, remember, K for electrostatic is equal to 1 divided by 4 pi epsilon naught q prime, and for gravity, this is given by minus g m prime. Okay. Then what I can do from here, definitely the force of electrostatic can be written as minus gradient of phi, which I will call it phi electrostatic. And force, the magnetic one, the gravity one, it can be written as minus gradient of gravitational scalar, okay, or a scalar that defines for gravity. Okay, so now the question that I have is that what are the forms for phi g and phi e? Now I am looking for the scalar, looking for these scalars. Okay, what are the forms of these? So, well, I asked you last time, what is going on with the gradient of 1 divided by r? Do you remember? We did a calculation of this. Do you remember the result? Exactly. The gradient of r, 1 divided by r, let's do the calculation. It means that you have an x hat derivative with respect to x of r power of minus 1 plus y hat derivative with respect to y of r power of minus 1 plus z hat derivative with respect to z of r power of minus 1. Okay, so the first one will be equal to x hat. R, remember, was x squared plus y squared plus z squared power of 1/2. So r minus 1 means that you have minus 1. So you take the derivative of r minus 1 with respect to x, means that you have to take the derivative of these, which is minus 1/2, and then you have a 2x, and then you have the entire of these minus 1/2. So it will be x squared minus 1 plus y squared plus z squared power of minus 1/2 minus 1. So that is r power of minus 3. Okay. And the 2 goes away, so then you will have minus x divided by r power of 3. So the entire of these will be x divided by r power of 3 with a minus sign plus y hat y divided by r power of 3 plus z hat z divided by r power of 3. So if you write it down, you will get minus x hat y hat z hat, that is a r vector divided by r power of 3. So gradient of 1 divided by r is equal to minus r divided by r power of 3. Remember this because I will be using it today a little bit. Yes, Isa is asking about the minus sign. We discussed that so many times. I say that, well, this minus is not necessary indeed. So curl of a gradient is equal to 0. Either you have a minus sign there or you don't have a minus sign, for sure. We put this minus sign just to have a convention that things are falling down from higher potential to lower potential, just to tell that. Okay. So indeed, now if you look at the form of the force, which we had was kr divided by r power of 3, then instead of r divided by r power of 3, I can write as k, and replacing it, you will get minus gradient of 1 divided by r. So k is constant, I can bring it inside of the equation, I will get minus k divided by r. So remember, that's a scalar quantity. So force is given by minus gradient of a scalar quantity, which is k divided by r. I call these the potential or scalar potential. So for electrostatic, this potential is given by k, which is q prime divided by 4 pi epsilon naught, 1 divided by r. Remember, that's a scalar. The beauty is that. And for gravity, that is given by k divided by 1 divided by r, which is minus g m m prime 1 divided by r, which is a beautiful example that we may face. Guys, remember that in the equation that I have written here, okay, this is r vector, means that that's x hat, y hat, plus z hat. Some book, they write this, which is identical, k, so they write the force as k r hat divided by r power of 2, okay? Some people, they use it in this way, which is indeed is essential, identical, because r hat is r vector divided by its magnitude, so it's r vector divided by r power of 3. That's identical, so it's the same. So why we care about the scalar potential? Scalar potential that you do have, which is phi equal to k 1 divided by r, or simply k divided by r. And remember, force is given by minus gradient of potential, which was given by minus k gradient of 1 divided by r, which again was k r divided by r power of 3. Okay, all of them, they are identical. Where did we get this? Because curl of f was equal to 0. Lovely. Now, using this property, I'm asking you to do the calculation and find out for me what is happening with the work. What was the work? Was the force multiply or dot product by the displacement. Okay, and a closed loop. So I can use the Stokes theorem. So I can bring the integral on a loop into the integral on the surface, which means that I will get curl of f dot d sigma, which is the surface that you have it. And that's a curl of the force. And as a result, we know that that's on the surface, by the way. So indeed, just having a geometrical picture. So I'm moving an object in a closed loop. So I will take this object, I will move it around, and I'm coming back to the same place. So I create a surface here, which if I move the object in this way, oh, sorry. If I move the object in this way, then the normal to the surface will be like this. So that will be n hat dA, which is equal to d sigma. Then using the Stokes theorem, I can bring the integral on a loop into integral on the surface, and then I will get the curl of f. And curl of f for this region, remember, curl of f for this region is equal to 0, then the entire result is equal to 0. So the work for the forces, when the curl of the force is equal to 0, and a closed loop is equal to 0, as Isa mentioned properly in the Q&A. Lovely, that's wonderful. So now I understand that if I take a force, I can check it. If the curl of the force is equal to 0, then definitely work of this, due to this force, work of this force on a closed loop is equal to 0. So, and what does it mean in terms of the physical meaning is that, well, I can split. So as a result, I have the work on a closed loop is equal to 0. So I will split these into two ways. I will say that I will take from the point of A, which I will do a rotation on B, and then I will come back to the point of A. But now I have two paths, path number one as path number two. So indeed, what I am doing essentially, I will move from the point of A to the point of B, but now I will take it from path number one, or I can take it from path number two. Pay attention to the arrows. I will go from A to B, but from being the work on the closed loop being equal to zero, then I can write these as integral of from A to B on path number one, f dot dr, plus integral of, on the closed loop, I'm writing on a closed loop, from B to A on the path number two of f dot dr is equal to zero. Okay, this is what I will get. So, however, remember that going from B to A is equal to A to going to B from the path number two with a negative sign. So that is equal to minus integral of f dot dr from A going to B, but on the path number two. So indeed, what I will get as a result, that integral of f dot dr, A bringing A to B from path number one is minus integral of f dot dr from bringing object from A to B, but on the path two is equal to zero, and therefore I will get integral of f dot dr bringing A to B, either from the path number one is equal to integral of f dot dr bringing A to B on the path number two. So if kernel of f is equal to zero, then I will get integral of f dot dr is equal to zero on a loop. And from this, what I will get, that the work is independent of the path that you choose. One may choose. Okay? And we call these kind of forces conservative forces. And the two examples that I provided here, they have these property, gravity and electrostatic. So they have this property, which the kernel of f is equal to zero. So they are independent of, essentially independent of the path that you take the integral. Okay. Any questions so far?
Good evening, Professor.
No questions? Okay. And remember, the force was given by minus gradient of a scalar. Let's see it from a different perspective. Why? Okay, I understand that the force, the work due to the force on a loop is equal to zero or is independent of the path that I will move. But let's see explicitly what is the work associated to that. So what is the work, the exact value of the force, of the work that I have. So what I'm asking, so I am bringing the object from point of A to point of B on one of those paths that we explained. And now I'm calculating what is going on with f dot dr. Okay? That's the work that I'm looking for. So f is given by minus gradient of a scalar, okay? So what is happening with f dot dr? What's that? Is equal to minus gradient of phi dot dr. What is this value? Can you write it in a Q&A, please?
Sorry, Professor.
Yes.
We have only one question.
Oh, yes, I will answer to that question. So now let's go for the answer. Yes, exactly. Mobin say it correctly is d phi. Mason also they say that is d phi. So perfect. So that is equal to minus d phi. So the work that I have, which is bringing the object from point of A to point of B. Point of A means that you have RA, and this one also is RB. F dot dr is equal to minus integral of gradient of phi dot dr from RA to RB. Even you can write it as a vector. That is equal to minus integral of d phi from RA to RB. And then integral of a derivative, what's that? The result is phi, right? So that will be minus phi from the interval of RA to RB, which the result will be equal to minus phi, calculating the potential at the point of RB, minus potential at the point of RA. Okay, some people, for simplicity, they write it as minus phi B minus phi A. Okay. D phi, we define that. So, well, phi is a function of x, y, and z, right? If you remember, right? Look at the previous lecture. And we look at the infinitesimal changes in phi. So then is the argument of x, y, and z. So what you have to do, you have to look at the changes in x, changes in y, changes in z. So d phi is essentially derivative of phi with respect to x. When you have a small changes in dx, derivative of phi with respect to y. When you have a small changes in y, derivative of phi with respect to z. When you have a small changes in dz. And if you look at this is essentially gradient of phi dot dr. Okay, good, perfect. No questions? Yes,
There's-
yeah, perfect.
Sorry,
Yes, go ahead, please.
we have only one question.
Okay.
From Isa Muhammad. So work depends only on the endpoint of the path.
Yes, indeed. So, well, this is what I want to say here. We calculated the work, right? From A to B. And then what is we realized that the work, if, remember, if f is given by gradient of a scalar, is given by the value of the scalar at B minus the value of a scalar at A, okay? So it all depends on the initial point and final point. So let's look at this. Again, I'm writing it down because it is important, not in general that is valid. If curl of f is equal to 0, then means that f is given by minus gradient of phi, right? And also from that point, what I understand that integral of f dot dr is equal to 0 and a closed loop. Then what I realized that integral of f dot dr from the point of RA to point of RB is, which is the work, is equal to minus phi B minus phi A. So phi B means phi at RB, and phi A means RB, that is phi at RA. Now I want to clarify what is happening with the minus sign, okay? Why we had the minus sign here. These minus sign that each lecture I'm asked to explain it, okay? So this is the earth, okay? The floor that I have it, or you have it at home. And I want to move an object, or let's move having an object moving from the height of h to height of, let's say, h capital, to the height of h small, okay? Lovely, okay? So the point that here we have is z at the point, well, you can fix x and y, and then for the z you have only that one, z hat h, and for this one you have z hat h small, and we know that h is greater than h small, okay? Lovely. So I'm asking you, if I have an object, I want to bring it from h small to h higher. Should I do a work, or is a positive work, or is a negative work, or is it happening by itself? Is a positive force, exactly, because what is happening, the potential that I have is given by indeed is given by mgh, right, or mgz, let's call it in this way. And for the point of A, which is that point, I have mgh, and for the other one, phi b, which is the endpoint, I have mgh capital. So the work that I have to apply to moving from the point of A to the point of V is equal to minus mgh minus mgh. Oh, sorry, then I have a minus direction as well. Okay. So it's minus plus is mgh minus h. So if I want to bring it from the point of A to the point of B, indeed you need to apply positive a work to do this job. Okay. So, and you see, it doesn't matter. You can bring it out of the plane and then moving around and bringing it to the point of B. So it doesn't matter. You can go straight up or you can go on a path. So this is the conservative force that we are facing, and this work is independent of the path that you do the work. Okay, so that's an important concept. And now I think you are satisfied that you have a minus sign here. Else, if you don't have a minus sign, you will be in trouble. Okay, because water does not go upwards, as it was explained by one of the students in the Q&A. Clear? Good. So if this is good, now let's go to the vector potential. That was a form of a scalar potential. And remember, in order to introduce that, you need to have the curl of the force equal to 0, which means that the force is given by minus gradient of something. And that is also true for example, for electric fields. So I'm not necessarily working with the field with the force, but you can work with electric field, which is exactly the same concept. So it's just reduced by a factor of Q. Now let's go with the scale, the vector potential, which was given by curl of A. Okay, so we had curl of A, which was given by it was giving us the magnetic field. So where did we obtain this? Divergence of B was equal to 0. And we say that when the divergence of a vector is equal to 0, then you can write this vector as a curl of another vector. Okay? And that was wonderful. Okay? So, and we call these vector potential. Remember, in the case of scalar potential, F was given by minus gradient of a potential. Here is a scalar. Dealing with a scalar is very easy, is the same algebra that we are dealing with. And what you have to do, you have to find the scalar potential, and finally you will take a gradient of that and you will get the force. Here, no. B is a little bit complicated. Calculating B by itself, you use the Biot-Savart law, for example. Calculating B is complicated. But even you can use this law, which is the divergence of B, and then you can introduce another vector A, and then that even simplifies your calculation way much, okay? It's way easier to calculate A rather than directly going with B, okay? But remember, A still is a vector, but a vector that can be calculated easier. So, well, curl of A is equal to B. What does it mean? Well, B is a vector. I can write it as a B1 x hat plus B2 y hat plus BZ z hat, which remember that B1, B2, and B3, in general, they are not 0. And in general, they are functions of x, y, and z. So they are functions of the coordinates, so they can move. Point by point, when you move them, you will see the value is changing. What is the general formalism also for A? A also is the same. So it can be A1, x hat, A2, y hat, AZ, z hat. What are the conditions for B? Divergence of B should be equal to 0, as we know. Means that the derivative with respect to x of B1 plus derivative with respect to y of B2 plus derivative with respect to z of B3 is equal to 0. On the other side, there is a relationship between A and B. What is this relationship? Curl of A must be equal to B. So means that B1, I will write it down. I will write it in terms of Levy-Chita notation. Let's say write it. Wow. So means that Bi is equal to summation on J of epsilon I J K, a derivative of J A K. So you can do the expansions, and what you will get the B1 is equal to derivative with respect to Z of a, sorry. Derivative with respect to Y of A3 minus derivative with respect to Z of A2. And B2 is derivative with respect to Z of A1 minus derivative with respect to X of A3. And B3 is equal to derivative with respect to X of A2 minus derivative with respect to Y of A1. Okay, Lovely. So now I have three differential equations, partial differential equations, which they are telling me how to calculate A1, A2, and A3 from B1, B2, and B3. Good. Agreed, guys? Okay, perfect. So how can we determine these? How can we find these A1, A2, and A3? The first question that I'm asking you, and you can write it in Q&A, is A unique? Mobin say no. No, no. Okay. So all of you, at least so far that I see, all people, they are saying no. A is not unique. We up to a constant. Some people, they say that up to a constant. Okay. No, I don't agree on that. You will see that what I mean. What is happening? By the way, don't forget what I want to do. I want to calculate A from B1, B2, and B3. But now I'm telling you that I have to consider something with A's. Else is a little bit difficult to go and find it out. And I will tell you that A is not unique. So why A is not unique? What is the only condition that I have? Curl of A is equal to B, which means that divergence of B is equal to 0, which means that the divergence of curl of A is equal to 0. Lovely. Now I'm saying to you, change A to any A plus gradient of lambda. Yes, Amir Hossein is correct. So let's do that. Instead of A, I will write A plus gradient of a function, which this function is a lambda, is a scalar quantity. So curl of A plus gradient of a lambda. Remember, lambda is a function of X, Y, and Z. And we assume that there are derivatives exist, so is will behave function. So curl of A, we have the result curl of A plus curl of a gradient of lambda. What is a curl of a gradient? Nuria says 0, Maysem says 0, while he says, well, Mobin, Sergol. Yeah, perfect. I mean, lovely. So you got the point. This is equal to 0. So means that I have again curl of A. So this is B. So B is invariant under this transformation, the following transformation. What does it mean? That you can take any potential changing to that potential plus gradient of a scalar, and still you will get the same magnetic field. So, well, yes, you can say that it's unique up to a gradient, but that's not anymore unique. So you have a gradient that you can add it. That can be any vectors that you added there, but these vectors is given by the gradient. So going back to the question that I had here, well, lovely. Here means that A A1, A2, A3 that I want to calculate it from B1, B2, and B3, well, they are not unique, okay? So you have to assume something. I can assume something, right? The first thing, let me write it down here. So I will write down B1 is equal to derivative with respect to y. I go with the mathematical notation. So this means that derivative with respect to y, okay? And that is A3 minus derivative with respect to z of A2, derivative with respect to z of A1 minus derivative with respect to x of A3, B3, that is, I have derivative with respect to x of A2 minus derivative with respect to y of A1. Okay, lovely. So I have these three equations, but now I know that I have a little bit of freedom on choosing the A. I have some freedom. For example, I will choose A1 equal to 0. That's a choice. You can choose A2 to be equal to 0 for simplicity. So let's do that. And what I will get from here, I will get B1 is equal to derivative with respect to y of A3 minus derivative with respect to z of A2. And then from here, what I will get B2 is equal to derivative with respect to z of A1, which is 0. Then I will get minus derivative of x of A3. And B3 is equal to derivative with respect to x of A2. Okay, no questions? Good. Now, what do we know? We know B1, B2, and B3. What we are going to find? We are going to find A vector. And we assume that A1 is equal to 0. And we want to solve these equations. So how do you solve the first equation? Or the second equation? Yes, I'm making an example. I'm making an example, but I will choose the freedom that I have. How do we solve A3? So from the second equation, I can find A3. What is A3? A3 is the integral of, with minus sign, of course, B2 dx plus a constant. Do you agree? Lovely. Okay, fantastic. What about A2? Is integral of B3 dx plus another constant. I will call it d. But do you agree that C and D, they are constant? Do you agree? Constant with respect to what, guys? I'm adding these here, right? What do I mean? Exactly. So it means that is a constant with respect to x. So it means that it's not a function of x, but it can be a function of y and z. It can be a function of y and z. True? Lovely. Mobin got that, and many other people as well. That's fantastic. So A3 or A2 is equal to integral of B3 dx plus d of y and z, and also A3 is equal to integral of minus B2 dx plus c, y, and z. Lovely. So from by and bz, I can find A2 and A3, which is ay and az. That's lovely. What about A1? Still, I have to, I got A1 as well, which is equal to 0. But there is still one problem. What is the problem? Do I know the constant functions? If vector potential is not unique, then how do we measure it? Oh, well, we will discuss that. Yes, exactly, Isa. So Isa is saying that, well, still A2 and A3, they are not clear to us because we don't know what is D and what is C. How do you find D and C? Exactly, Mubin says that we have to replace A2 and A3 inside of this equation. So let's do that. So we are replacing these two inside of the equation that we are using B1. So is the derivative with respect to y of A3, which is minus integral of B2 dx plus C of yz. Remember, now is a function of y and z. And then I have the other term, which is minus derivative with respect to z of integral of B3 dx minus plus dy and z. Lovely. So from these two, I have to find out what's going on with the d. So let's substitute it inside of this and let's see what we will get. So we will get minus integral of derivative of y of b2 dx minus integral of derivative of z of b3 dx. Then I have plus derivative of y of c minus derivative with respect to z of d. Good? So far, so good, right? I can pass them together. So from B1, I have minus integral of derivative of y of B2 plus derivative of z of B3 dx plus derivative of y of c minus derivative with respect to z of d. Good? I get something complicated. Any idea how to replace these, guys? Because remember, what's that? Is derivative y, by. Derivative of z, bz. They are by, b2, b3. And is getting a little bit more complicated. I have to use another property to simplify this. Any thoughts? And no, but not boundary condition. No, not Stokes theorem. Exactly. Baran got that. Amir Hossein also they got that. So remember, at the beginning, I said to you, what is the relationship? Divergence of B is equal to 0. Don't forget that what you started with. So divergence of B is equal to 0. Means that derivative with respect to x of B1, derivative with respect to y of B2, plus derivative with respect to z of B3 is equal to 0. So means that the derivative with respect to x of B1 is equal to minus derivative of y of B2 plus derivative of z of B3. Good. So then instead of this, I can write the derivative of minus derivative of x of B1, or with minus sign, you will write it as a plus. So you will have a B1 equal to integral of derivative of x of B1 of dx plus derivative of y of c minus derivative of z of d. What is this? No, there is no minus sign. Remember, the entire the minus sign goes away with the other minus here. Is B1, exactly. You will get a B1 plus derivative of y of c minus derivative of z of d. Okay? Beautiful. So B1 is equal to B1 with this term. So this term, it should be essentially equal to 0. So, and then you can just find out, for example, you have a freedom on choosing the D and C. For example, you can keep one of them to be equal to 0, and then you will find the value indeed. Okay. I hope that is clear now. Good, perfect. So that's a vector potential, and vector potential also is very, very important, as I say, during the previous lecture. So people they use, I mean, mainly it appears in quantum mechanics and has a physical meaning as well, as I described during the previous lecture in a Harlow bomb effect. And it's very important to consider and learning these properly. I will encourage you to look into the Schrödinger equation. When Schrödinger equation is written for a place that there is an electromagnetic field. And when you write this, you will see that you have to go and rewrite the Schrödinger equation in such a way that it explains also the electromagnetic interaction. And you will see that the vector potential appears in the calculation, and you have to do some sort of transformation for the wave function. In your book, there is this example, but I will not discuss that because it's getting a little bit more complicated, okay? Or maybe it's beyond the scope of this discourse at the moment. So now I will, during this, let's say, almost 50 minutes, 55 minutes, I will be going to use the Helmholtz theorem, which is using the green function, because there were one question related to that they did not understand the green function properly. So in order to describe this, well, let me introduce a function, okay? So hereafter, it's a completely new topic. So do you remember that we discussed about delta Kronecker? Delta. And we say that this Kronecker delta is determined in a discrete space. For example, we had two indexes of I and j, or two indices of I and j, and we say that when I is equal to j, this is equal to 1. When I is not equal to j, that's equal to 0. And that was a delta Kronecker, and it was wonderful because we could write the orthogonality relationship, or we could simply using it in reducing the summation. For example, if you had xi delta of ij and the summation was or I, then the result was simply xj. Okay. Or when you had two functions that they were orthogonal to each other, then simply you will get delta of ij. When we want to take the derivative of x1 with respect to x2, that was simply delta of 1, 2, or delta derivative of xi, xj, that was simply delta of ij. We say that this is equal to 0 unless I is equal to j. So it was a very useful function that was determined in the discrete space. Discrete space means, remember, was 1, 0, -1, 2, -3, -2 and 3, and etc. So that was defined for an integer quantity, okay, in the space of Z. I and J, they were element of Z. Now I will introduce another function that this function is zero everywhere, a zero in space, unless x is equal to 0. Okay, so that is 0 almost when as x is not equal to 0. But when x is equal to 0, well, loosely speaking, I would say that is infinity. Okay, well, I have to go approximation. So what does it mean? So this is defined in a real space. So it means that it is not discrete space, but is a continuous space. So that's x. And now I'm looking at the delta function. So everywhere is 0, except here, except x equal to 0, that's going to be infinitely large. Let's introduce it for another space. So delta of x minus x0, the same way. We say that when x is not equal to x0, that is 0. When x is equal to x0, that's infinity large. So it means that if that point is x0, everywhere is 0, except this place, which is going to be infinite. And we call these delta Dirac. This is not the only property. The property is that integral of these, Riemann integral of these, so integral of delta of x dx on all space is equal to 1. That is true that this function everywhere is equal to 0, except x equal to 0. But when you look at the surface, it is such a way that is normalized to 1. Okay? Let me introduce it in a simpler way. At least you will have a feeling about it. Assuming that I have a function this function, I will call it delta, has a length. This length is a minus a divided by 2 and a divided by 2. And the height of this function is equal to a. Oops, sorry. I'm not good at the geometry. So it should be twice of that. So that is a. So this function of delta, I introduce it in this way. So this delta that I introduce, I say that delta of x has the following property. When x is smaller than a divided by 2 with a negative sign, is 0. Okay? When x is greater than a divided by 2, which is this part, is again 0. But when x is between these two, has this value. When x is between minus a divided by 2 and a divided by 2, that has the value of a. Okay? Yes, it means the probability or the surface here, indeed. So can you tell me, guys, what is integral of delta x dx in all space? All space means integral of delta x from minus infinity to plus infinity. Oops, sorry guys, is a squared. I think I did a mistake. Let's go with 1 divided by A. Now, can you tell me what is the value? Mobin, you were right. Redmi, also you were right. So now I'm changing my mind. I did a bit of mistakes. Okay. Amir Hussein, right. Mobin, right. Nuria also is right. So the value of this, which is the surface, indeed, you will get 1. Because it will be the length that you have it here. So that will be the surface that you have. That is the area. So the length is A, and the height is 1 divided by A, and multiplying these two together, you will get A multiplied by 1 divided by A, and that is equal to 1. So that function, this delta that I define, by the way, is a function of A as well. I can write it in a compact form. I will write it in this way. When absolute value of X is smaller than A divided by 2 is 0, is equal to 1 divided by A. When absolute value of X greater than A divided by 2, that is equal to 0. So this is the function that I determine. Now, assume that we go for a case that A is equal to 1. What I will get as a form of the function? The function that I have is 1/2 here. It is 1/2 here, is a negative sign, and that would be 1 here. So that's the form of the function that I have. When A is equal to 2, then what I will get? Oh, let's go with A, which is equal to 5. Let's get 10. A is equal to 10. When A is equal to 10, I did a mistake. 2, 1. Let's go with A, which is equal to 1 divided by 10. So then that will be equal to 0.25. That will be A divided by 2 will be equal to, let's go with, that will be equal to 1 divided by 20 with a negative sign, minus 1 divided by 20. And that side will be equal to 1 divided by 20. And the height will be equal to 10. So that is 1. Essentially, you have to go up to 20. So 1, 2, 3, 4, 5, 6, whatever. So I'm assuming that's the value. So that is the value that I have for this. Assuming that it is equal to 10, because it's going to be 1 divided by A, and 1 divided by A is equal to 10. Okay. So what happens when A going to be extremely small, A to be extremely small, then you will see that in order to keep the area to be a constant value of 1, then the height should be increased. And asymptotically, we can speak that this function, when you take A to be 0, then asymptotically this is equal to delta of X. Okay? And we call these delta Dirac function, which, as I say, that we will be using it a lot in physics. So I hope that at least you will have a feeling about the delta Dirac function. And there are many different ways that you can introduce delta Dirac function. You can go with the Gaussian distribution. You can go with Lorentz distribution. You will go with the sinc function as well. So there are many different ways that someone can introduce the approximately the delta, the Dirac delta function. And but the property that I want to say that remember that delta of x minus x0, this is equal to 0 when x is not equal to x0. When x equal to x0, that is equal to plus approximately infinitely. Integral of delta of x minus x0 dx in all space is equal to 1. So you may ask, what is happening if the delta of x minus x0, if you do the integration, is not including the x equal to 0? So for example, integral of delta of x minus x0 from x, I will call it from interval of a and b, and a and b, let's call it this interval, does not include x0, okay? Oh, x0 is not belonging to this interval. What is the result? For example, exactly is equal to 0, assuming that we have the delta Dirac, which means that that's a point of x0, right? And I'm doing the integration in this interval. So of course, that's not including the x0, so the result will be equal to 0. Lovely. So I think you got the feeling. So what is happening with integral of fx delta of x minus x0 dx? Look like the delta Kronecker. Do you remember delta Kronecker? We had this property. The summation of delta of ij xi was given by xj. And here the same property we will have. So what we can do, that's in all space, or indeed in the space, or in a space that includes x naught, then what I can do, I can say, well, just if that's x0, then I will go epsilon smaller than x0, so that will be x0 minus x epsilon, and that will be x0 plus epsilon. So everywhere that will be minus infinity to x0 minus epsilon, f of x delta of x minus x0 dx, and then I have plus integral of x0 minus epsilon, x0 plus epsilon, f of x delta of x minus x0 dx, and then plus integral of x0 plus epsilon plus infinity f of x delta of x minus x0 dx. So we know that for these two regions, which is not including the x0, that will be equal to 0, and the last one, that will be approximately speaking, delta will you evaluate it at the point of f equal to x0. That will be the result that you expect to receive. Okay, and but that is for the case when epsilon goes to 0. Lovely. So I see that many people, they write it in a proper way. Wonderful. So there are some other properties of the delta function. So delta of a times x. So you want to understand what is the relationship with the if the x has what is the relationship with the delta of x? So I want to find out what is the relationship if the function has an argument. I will tell you, Baran, the physical explanation of delta Dirac function. So integral of delta of ax dx. I want to understand what's going on with the relationship with the delta of x. What you have to do now, you have to do the change of variables. So you consider that ax is equal to u, and now you have a dx equal to du, and then you have integral of delta of u, and then instead of dx, you can replace it by du divided by a, which is 1 divided by a of integral of delta of u du. Now there is a problem. What is happening with the interval? Then we have to consider that I is either positive or is negative. So it depends on the value, the interval will be flipped. So indeed, the result that you will get for this, it will be 1 divided by absolute value of a. So you have to do the calculation properly. As what I have done here, it was for a positive. As an exercise, do it for yourself when a is negative. Okay. So, well, there are many examples about the delta function. I gave you a few of them as an exercise. I will encourage you really to do the homework and learn about the delta Dirac function. But let's look for the physical meaning. Assuming that I have a charge in space, okay, that's the 3-dimensional space, x, y, z, and this charge has a value of q. What are the charge density, okay, in space? What is rho in space? It is 0 except this point, right? It is 0 except r, let's say 0, okay? Okay, so a rho of r is equal to 0 when r is not including r0. Okay, what is happening when r is equal to r0? At the point of the charge, what is the charge density? Is infinity, right? At the point of the charge, what is the charge density? Because the local point is, and then you expect that the charge density will be infinity. I'm not talking about total charge. I'm talking about the charge density. But I know that integral of rho r dv, the integral on whole space, is equal to how many charges exist there? What is the result of this? Goer? Yes, she said that is Q. Exactly. So the total charge in that space is Q, right? That's the total charge that I'm expecting to see in this space. So indeed, the total charge is Q. So what is the function that I'm expecting to be 0 everywhere except one point, which is R0? But if I do the integration on the space, that will give me a value of the Q. So indeed, that is Q delta of R minus R0. Okay, exactly. Mobin wrote it in a proper way. So this is the charge density. Lovely. So the charge density indeed, in one dimension, if you determine the, let's say, this is what we call it in physics 1, if you remember. In physics 1, lambda x was given by Q delta of X. So that is the charge density on a line. Okay. Sigma of, let's say, X and Y. That can be Q delta of X delta of Y. That is surface charge density. Surface charge density. And rho of X, Y, and Z. All of them, they are for point charges. It's Q delta of X, delta of Y, delta of Z. That is the volume charge density. So here you determine it, the charge at the origin, and you call it Q. In the second scenario, you go with X and Y dimension, and you place the charge here. In the third scenario, the charge is located at the origin, which is X, Y, and Z. Okay. If you move them to another place in space, for example, if you move them to x0, then the first one becomes lambda of X, which is the Q delta of X minus x0. This is the place that the charge is located, which means that it is not located at the origin, but is located at the x0. For the other one, you can place the charge here, which is at x0 and y0, or you can place it in space, which is given by x0, y0, and z0. Okay. And all of them, they are sigma x, y, which is Q delta of X minus x0, delta of Y minus y0, and delta of Z minus, sorry, we don't have that. And then for the charge density of X, Y, and Z, we have Q delta of X minus x0, delta of Y minus y0, delta of Z minus z0. So usually we call these the one-dimensional delta. Together these, we call it two-dimensional delta, and together we call these three-dimensional delta. And remember, what is the dimension of delta function? Is it in centimeter, is in meter, is in second? What is the dimension of the delta? So integral of delta of X dx is equal to 1. What is the dimension of dx? Is length. So what is the dimension of this? Should be, it should be 1 divided by length. That's the reason that is equal to 1. So what is happening with the two-dimensional space? With the two-dimensional, that is 1 divided by length, 1 divided by length, and that is equal to 1 divided by length power, which is L minus 2. And for this one will be L minus 3. Remember, the integral on the surface, integral on the volume should be equal to exactly. Halala also say that is correct, Muhaddisa as well. So the probability should be equal to 1. So means that whatever you do the integration there, which is d volume, then the delta should have 1 divided by the volume dimension, which is L power of 3. So it will be L power of minus 3. You can see these also from the delta that I determined, delta of AX. If you remember, that was equal to 0 everywhere, except the interval of X smaller than 1, what was A divided by 2. And that was equal to 1 divided by A. So if you have A as a dimension, that will be 1 divided by length as a dimension that you may expect. Wonderful. Good. Now I know a little bit about the delta function. I will ask you kindly to look into the description. And as I say that you can have a one-dimensional delta function, and the one-dimensional usually you write it as a x minus x0, but also you may have a three-dimensional way, which is x minus x0, delta of y minus y0, delta of z minus z0. And usually we write it as a delta of r minus r0. And this is a three-dimensional delta. We can write it as integral of delta of r minus r0. D volume is equal to 1 if that includes all space. That's a short notation, but indeed this means the entire day's integral. Okay. Wonderful. And deltas are very important. You can define it even in terms of orthogonal functions, and you will see that they are extremely useful in algebra. Now I will go with divergence of E. Okay. Or even before doing that, I can introduce another function, which I will call it solid angle. How do we define angle? I mean, this is what I define it angle. It will be usually on a surface. So I say that an object is, I'm observing here. This is me, observer. I see a point and I see another point. I will make a line, okay? And then I have a distance from these two. Then I define what is going on with the length divided by the distance that I have. So angle approximately, if you want to define it, it will be the distance that you have it here, delta divided by the distance of the 2 points. So this is the angle that you determine it. And if you want to be a little bit more careful, what you have to do, you have to make a circle. Essentially, what you will do, that distance will be projected on the tangent. And indeed, if I look at from the top side, you will see that essentially from the point of A to the point of B, then you make a line, and then the points of observation, which is O, and the distance that you have, it is R. Indeed, the angle of theta is defined as, roughly speaking, AB divided by R, or delta divided by R. And this is what we call the in plane angle, and it's introduced in terms of radian. And we are using it in geometry easily, but we can use the same concept and introducing a new quantity, which we call it the solid angle. And this solid angle is not defined as the length divided by the distance, but is introduced as the surface divided by square root power of 2 of the distance. What does it mean? Well, assuming that I'm in the 3-dimensional space and I'm looking at the screen, I know the distance from the screen, and I know the surface of the screen, which is orthogonal to me. Remember, that should be orthogonal. And if the surface is S, then essentially the solid angle is given by S divided by R power of 2. So if I change my orientation, assuming this is a classroom, right? If this is a classroom, and that's a blackboard that I have it here, some student, they may go to edges, they may go here, and they can look at the screen. even at the same distance. So assuming that these r is the same. So what you do, you move to the side, and what you will see, you don't see the screen in a better way. That is related to the solid angle that you observe it. That's the reason that in most of the classrooms, most students, they are mainly at the center because they have a better vision, because they have a higher solid angle. So I hope that the solid angle is clear for you. So what is the dimension of the solid angle? Solid angle is given by surface, which is L square, divided by the distance power of 2, which is L square. So the dimension is equal to 1, has no dimension essentially. It's not dimension 0. We call it that has no dimension, or is dimensionless, and we call it with stradian. Okay. No, I have written with Y. And now, assuming that I am in space, and I look at the entire my, let's say I'm in Ottawa, let's say, or I'm in Erbil, and I'm looking at the sky, right? So this is me. I'm looking the entire of the sky. So what I will choose a distance of r, and I will make a surface with this, and the surface that I have is a hemisphere, right? What is the surface of a hemisphere, the value? What is the surface, the total surface? Can you write it down? The total surface of a sphere with a radius of r is 4 pi r power of, who wrote r power of 3? Is r power of 2. So, and then the half of these, it will be 2 pi r power of 2. Do you agree? So that is the surface that you have, it is 2 pi r power of 2 divided by the distance that I have, power of 2, which is r2. So you have 2 pi stradian. So that will be the half solid angle that I see. If I include the lower part, assuming that you bring me up with an helicopter up, okay, and then I look at the solid angle that I see, or the full solid angle that someone can see it, it seems that this person will see a sphere, and the sphere surface, the full solid angle, is 4 pi r squared divided by the distance, which is r squared, which is equal to 4 pi stradian. So the entire space is 4 pi stradian, and that's in the 3-dimensional space, right? In the 2-dimensional space, if we introduce, do you remember? We say that, well, you have a plane and you do a rotation around that. So it will be a radius of r. The perimeter is equal to 2 pi divided by r. So it will be 2 pi divided by r, which is equal to 2 pi radian. So in the 2-dimensional space, the whole angle is 2 pi radian. In the 3-dimensional space, the full space is 4 pi stradian. So which is wonderful. Okay. Lovely. No questions? No question. Perfect. So remember, that was a case which I was at the center, and I made a surface around myself, okay? Or it can be a full surface. What happens if I'm watching a surface or sphere, let's call it, or a surface, a closed surface that I have, and I'm looking at the solid angle that I see this object? I'm looking at the Q&A. Yes, that is true, Isa. This full solid angle is what people, they use it in astronomy. Yes, in astronomy, they use that. In the definition that I have it for the Stradian or solid angle, usually we call it with omega, okay? Omega, the capital is the solid angle that we use it. Was surface divided by the distance power of 2. But we know that in the example of the students in a room, you will see that people, when they go at the corners in the lecture room, they will see different solid angles. So that was assuming that that was the whiteboard, and I'm watching it from this corner, assuming that the distance from here is the same for these places. All of them, they have the same distance of r. But now the observer is moving, is one of the students which is moving in the classroom, okay? They are moving in the classroom and they want to see what is going on with the solid angle. So what they will see that here, if you have a surface, if the surface is orthogonal to the observation point, which if the student is here and seeing this point, if the surface is S, then the solid angle for this observer, let's call it observer C, A, B, C, D, and E, for observer C is the entire of the surface divided by r power of 2. But what is happening with the observer A, solid angle for observer A? Observer A will see, if you look at me on the screen, you will see that, I mean, these are, I don't know, let me check, I cannot change the background. So this is a surface that I have, is a notebook. If you rotate it, if you tilt it, assuming that someone is watching not orthogonal, but is watching from the angle. If you watch it from the angle, you will see the notebook which is rotated. So the surface is not anymore this surface, but the observation that you will see, it's a little bit projected. So what is important here, that the normal to the surface, which is this normal, and normal to the point of observation, which is this one, also plays role. So when you tilt, when you go to the angle, then you will see that the projection of the surface onto that specific direction, reducing the effective surfaces that you have. So essentially, you will see here another surface, which is surface orthogonal to the r power of 2. And surface orthogonal is essentially S cosine of theta, which this theta is the angle between the normal to the surface and your point of observation that you will see, which that goes with r power of 2. And indeed, I can introduce even what is happening with the surface vector. If you remember, we say that you can define a vector which is orthogonal to the surface, and we call it with S vector, which is indeed n times S. And cosine of theta is the angle of r hat, which is the point of observation. So indeed, that is equal to S dot r hat divided by r power of 2. So that is indeed the solid angle that you will see. If you even consider the infinitely small solid angle of d omega that can be introduced by the surface, which is having a small value, which is ds or d sigma, dot product with r hat divided by r power of 2, or r hat can be even written as r divided by r, and that can be written as d sigma dot r divided by r power of 3. So recall that solid angle of d omega is integral of r, it's too early for introducing the integral, is r d sigma divided by r power of 3. So if you look at the geometrical picture, if you have an infinitely small surface, then you have d sigma, which is orthogonal to the surface, Then if I'm looking at the at that surface from the point of O, that is the point of observation that I have, then this point is R, and that direction is R hat. Then in order to do the calculation, what I have to do, I have to do R dot d sigma divided by R power of 3. So that will be the solid angle. So solid angle, like the angle in the two-dimensional space, can be negative, can be 0, can also be positive. Okay, so for example, in these example that I drawn here, solid angle is positive. But what happens if I'm looking at the surface, which is a closed surface? This is a closed surface. And I'm looking at this closed surface from this angle, this point of O. If I look at the one small region here, which is this small region, normal to the surface is this direction. So that's the d sigma. And the point of observation R is like this. So the angle between R dot d sigma is negative. So sorry, the angle between these two is more than pi divided by 2. Then I expected R dot d sigma is negative. Okay, so if I divide the regions in two different parts, so one is going to be the red part, which is showing the curvature towards me. For this region, the solid angle is negative, while for the other surface, which is on the back side, for the other surface, I have exactly the same solid angle, but dn here is in the opposite direction. Then I have the solid angle, which is positive. But I do see the same surface on the front and the back. So that for this specific geometry, or let's say specific object, if I look at the solid angle, the total solid angle is equal to 0. So which the total solid angle is essentially integral of d omega, which is integral of R dot d sigma divided by R power of 3. But for a closed loop, which this closed surface does not include origin. Origin means the point of observation. However, if this surface is coming towards the origin, right? So now I assume exactly the same surface is coming to the origin. And me, I am inside of this surface. What is the solid angle, guys? Now I am inside of this surface. Can you write it in the Q&A? Exactly, it's 4 pi. I can approximate it with anyway. So omega, if you do the calculation, that is equal to is not equal to 0 anymore, but is equal to 4 pi, which means that integral of d omega is in for this closed surface of R that d sigma divided by R power of 3 on this, when includes the origin, is equal to 4 pi. This is wonderful. What I see some sort of delta function that appears in my calculation. And I really like that. Indeed, I will go and I will write the equation in this form. Integral of R dot d sigma divided by R power of 3 can take two values. It can be 0 if the volume or let's say surface does not include, or let's say it's better to write the volume, it's better. If R equal to 0 is not included, no, sorry, to write the proper way. If R equal to 0 is not included, if R equal to 0 is included, is equal to 4 pi. Good, beautiful. Now I want to surprise you. Do you remember what was R divided by R power of 3? We just calculated this.
Dr. Ibrahim, I believe there's a small mistake in the R. You mentioned it's not included and it's included. I believe one of them should not be not equal.
Oh, no, no. No, that's correct. I say that R equal to 0 is not included in the volume. Okay. R equal to 0 is included in the volume.
Thank you.
Okay, sorry. I did, well, it was the little bit of yes, confusion there. So, well, people, they write it properly. So R divided by R power of 3 is essentially minus gradient of 1 divided by R. Do you remember, right? It was minus gradient of 1 divided by R. Agreed? Lovely. So integral, let's simplify this integral, and that will be the last thing that I will do. So this means that this integral indeed is equal to integral of R dot d sigma has two values, which we'll be discussing, but instead of R divided by R power of 3 dot d sigma, I will write the gradient. I will write as minus gradient of 1 divided by R dot d sigma. Agreed? Lovely. Integral of a or vector dot d sigma. What you will get from this? That's on the surface. Do you remember the Gauss theorem? Was integral of divergence of V on a volume, which this is created. That's the first thing that I had. So these are the first things. So I will be using that later on. But now going back to this integral of minus gradient of 1 divided by R, that d sigma is equal to either 0 or equal to 4 pi. So, and that's a surface, right? That's on surface. What does it mean? What is this value? Can you tell me? Yeah. Exactly. So the magnitude of that, it will be minus 4 pi divided by, well, no, I have to be a little bit careful. I have to be a little bit careful. Well, I will introduce that in the next lecture. It's too short. I have to go with the Laplacian now. So I will be discussing about that next lecture. But you are right. It's somehow related to oh, let's do that. Let's do that. So it doesn't matter. So let's go. Well, we have this value, integral of minus gradient of 1 divided by R dot d sigma. Okay. I use the Gauss theorem. And when I use the Gauss theorem, I will take the vector that I have and I will introduce the divergence. So it will be going from the surface to the volume that this surface is created with. And it will be divergence of minus gradient of 1 divided by r. And that is multiplied by the volume that we have, which is d tau or d volume. Doesn't matter, this is d tau. What is the divergence of a gradient, guys? Do you believe that this is minus exactly Laplacian? Minus Laplacian of 1 divided by r d tau. So since this is the scalar integral, I can do the calculation way easier. This scalar integral is equal to either 0 or 4 pi. So integral of something on the whole volume of V is equal to either 0 or 4 pi. Depending on volume includes r equal to 0 or the volume does not include r equal to 0. Okay, so definitely this should be a delta function, right? Delta of r function, which is a three-dimensional way. But the value is 4 pi, so do you expect that that will be equal to 4 pi? So then, as a conclusion, what I will reach to this conclusion that Laplacian minus Laplacian of 1 divided by r is equal to 4 pi delta of r. So which means that Laplacian of 1 divided by r is equal to minus 4 pi delta of r, which is an important relation that we obtain. Okay. Of course, I can write it down also as a divergence, but well, I will leave it to you. This is what today we want to obtain, and that goes back to the discussion that previously we had, and we say that in the electrostatic, if you assume that there is no charge in the space, the divergence of E is equal to 0. But on the other side, if you assume that you have a charge distribution, then the divergence of E is given by the charge distribution, which is rho. And as I remember, there's some people, they ask when I did the mathematics and I found the electric field for certain point charges, then when we take the divergence, we say that the divergence is equal to 0, except r equal to 0, which the charge was located. So if you include the charge location as well, then that should be given by the delta function, which we'll be discussing in the next lecture. And next half an hour, the next lecture, the first half an hour, will be going through the Helmholtz theorem and using some of those delta functions in distributing the charges and also doing a little bit of calculation. And after that, we will go with the curved coordinates. So I will stop here. Thank you very much, guys. And I'm sorry I didn't feel well today. I got a little bit confused sometimes. Thank you.